Have you ever stood in your local grocery store in the dead of winter holding a perfectly ripe, completely unblemished piece of tropical fruit and just wondered, how on earth did this get here? Seriously, how does a highly sensitive, highly perishable piece of fruit cross thousands of miles of unpredictable ocean without turning into a rotten, unusable mess? Well, it's a staggering logistical and engineering puzzle. We're literally talking about battling time, temperature, and the raw elements of the open sea, all just to keep our global food supply chain intact.
Welcome to today's Explainer. I'm absolutely thrilled you're here because today we are unpacking the marvel that is marine refrigeration. We're going to look at the blueprint of the modern reefer ship. Now, these aren't your standard cargo vessels. They are highly specialized floating thermodynamic fortresses designed specifically to cheat time and decay. We'll be digging into the science, the massive machinery, and the meticulous human effort that makes international food transport even possible.
Okay, so here's our blueprint for today. We'll be covering 1. Giant floating refrigerators, 2. 3 degrees of cold, 3. The science of cooling, 4. The clever brine grid, 5. The loading logistics, and finally 6. Surviving the cold voyage. Let's jump right in.
Section 1. Giant floating refrigerators.
When we measure the capacity of a reefer ship, we don't just talk about standard tonnage like we do with other vessels. Instead, we talk about cubic capacity. A typical modern reefer ship might boast somewhere around 600,000 cubic feet of cargo space. And here's why that specific measurement is so crucial. Every single cargo-carrying space on these ships has to be heavily lined with incredibly thick layers of insulation. That insulation is absolutely non-negotiable, but it also dramatically eats into the actual volumetric space available for the cargo itself.
Inside that insulated hold, the ship is essentially acting as a giant refrigerator. But here's the catch. You can't just blow cold air into a room and hope for the best. Cold air naturally wants to sink straight to the bottom, right? So to fight gravity and perfectly permeate the cargo, the floor of the hold is double-skinned. It features these precisely measured wooden gratings. That specific design allows cold air to be forced beneath the floor, where it then percolates upwards. So whether that cargo is loose in bins, stacked in boxes, or strapped to pallets, that upward flow ensures every single item is blanketed in the exact right temperature.
Section 2. 3 degrees of cold.
When you're shipping global commodities, you quickly realize that cold is definitely not a one-size-fits-all situation. We're dealing with 3 distinct categories here. First up is frozen cargo. Now, most microorganisms stop growing at -7 degrees Celsius, but we usually have to push it much lower. For example, high-fat items like ice cream actually require a freezing -26.1 degrees Celsius just to preserve their texture and flavor. Next is chilled cargo, where the outside might be frozen hard, but the inside is unfrozen. And finally, we have air-cooled or temperature-regulated cargo. This is where apples might ride at a crisp 1 degree, while citrus, like grapefruits, need a much warmer 10 to 12 degrees Celsius.
Now, managing those chilled and air-cooled categories is insanely difficult. For highly sensitive chilled cargoes, these containers have to maintain a microscopic 0.5 degrees Celsius margin of error. That is practically nothing. And it matters because at these temperatures, microorganisms can actually still grow. On top of that, as living fruits travel, they're naturally respiring and ripening, which produces carbon dioxide. If that CO2 builds up past just a 3% concentration, it'll literally suffocate and destroy the entire cargo. So the crew has to constantly vent the space and introduce fresh air, all without upsetting that delicate half-degree temperature balance.
Section 3. The science of cooling.
Before we go further, we actually need to redefine what cooling is. Scientifically speaking, you don't add cold to a room. Cold is literally just the absence of heat. So refrigeration is the mechanical process of extracting heat from the cargo space and then relocating that heat somewhere else. In the case of a ship, that usually means dumping it right out into the ocean or into the atmosphere.
Almost all marine refrigeration relies on something called the vapor compression system. It's a really elegant 4-step loop. Step 1, a compressor takes a primary refrigerant gas, something like R134A, and puts it under extreme pressure, which heats it up. Step 2, it flows into a condenser. Here, seawater cools that highly pressurized gas until it condenses into a liquid. Step 3, this high-pressure liquid hits an expansion valve, causing the pressure to rapidly drop. And finally, Step 4, as it enters the evaporator coils inside the cargo hold, that pressure drop makes the liquid rapidly expand back into a gas. That expansion is what violently sucks ambient heat right out of the air.
Looking at this setup, you can clearly see the continuous loop we just broke down. Notice the divide between the high-pressure side in red over on the right and the low-pressure side in blue on the left. The expansion valve is that critical gateway where the pressure drops, causing the liquid to evaporate and absorb heat from the cargo. Meanwhile, the compressor acts as the engine, pulling that warm gas back out and pressurizing it to start the whole cycle over again.
Section 4. The clever brine grid.
Okay, so that vapor compression cycle is perfect for your kitchen fridge, but scaling it up for a massive vessel, that presents a massive engineering headache. Pumping an expensive, volatile primary refrigerant gas all over a giant ship, which is known as direct expansion, is incredibly risky. Imagine trying to find a tiny, invisible gas leak in 600,000 cubic feet of cargo. No engineer wants to deal with that. So instead, they use indirect cooling. The vapor compression cycle is kept safely locked away in a small engine room, where it cools a massive tank of brine. This brine is usually sodium or calcium chloride mixed with fresh water, which drops its freezing point way below zero. This chilled, cheap, and super safe liquid brine is what actually gets pumped through the miles of pipes in the holds.
What's really fascinating here is how flexible this makes the ship. Notice how the primary refrigeration plant on the left is cooling a central supply of brine, but then that brine is routed through entirely separate, independent grid pipelines out to different compartments. Because they're completely separate, the crew can adjust the flow valves to keep one hold at minus 18 degrees for meat, while simultaneously keeping the hold right next door at a gentle plus 8 degrees for fruit. If one grid somehow gets blocked, they just redirect the brine. It's an incredibly resilient system.
Section 5. The loading logistics.
Now, all this amazing machinery is completely useless without strict human precision before the ship even leaves the port. Before a single box is loaded, the entire compartment, and crucially all the wooden dunnage and gratings inside it, has to be heavily pre-cooled. Why? Well, if the crew forgets to pre-cool the wood, it essentially acts like a hidden heat battery. The ambient warmth trapped in that timber will instantly transfer to the cold cargo the second they touch. That causes surface thawing, terrible condensation, freezer burn, and horrible staining that ruins the product. Shippers take this so seriously that frozen goods are often mandated to be minus 9.4 degrees Celsius or colder right at the exact moment they cross the threshold onto the ship.
Stacking the cargo is literally an exercise in exact geometry. The crew has to build perfect air channels that are at least 10 centimeters wide, but absolutely no longer than 3 meters, so the cold air doesn't get trapped. They also have to leave a very precise 30-centimeter gap between the top of the cargo and the ceiling. And here's a totally critical operational rule. If the loading hatches are opened, the refrigeration plant must be stopped immediately. Because if warm, humid port air rushes into a freezing hold, it instantly turns into thick frost on the brine pipes. And that frost acts as an insulator, completely destroying the pipe's ability to cool the room once those hatches are closed again.
Section 6. Surviving the cold voyage.
Once the hatches are sealed and the ship sets sail, the real battle begins. Deep inside the ship, there's this brilliantly simple device called the brine trap. It's basically just a U-shaped pipe filled with brine that drains water out of the cargo hold and into the ship's bilges. But it serves a vital dual purpose. First, that liquid plug completely blocks foul-smelling, dirty odors in the bilges from rising up and tainting thousands of dollars worth of fresh fruit. Second, it acts as a physical barrier that stops the expensive, heavy cold air in the hold from sinking down the drain and freezing the bilge water solid. It's a perfectly low-tech solution supporting high-tech machinery.
The officers monitoring these holds are dealing with some pretty terrifying exponential math. The general rule of thumb in refrigerated transport goes like this. For every 10 degrees Celsius, or 18 degrees Fahrenheit, that the temperature rises, the rate of food deterioration doesn't just tick up a little bit, it doubles or even triples. The decay literally compounds exponentially. Just a minor mechanical failure that raises the temperature for a few hours can trigger a biological chain reaction that rots an entire ship's worth of cargo before it ever sees a port.
The stakes here are unimaginably high. If temperatures swing too high, you get massive water loss, the production of ripening ethylene gas, and rapid, uncontrollable disease that just tears through the pallets. But what if you overcompensate and swing too low? Well, then you cause chilling injury, where the fruit literally suffers surface pitting, cellular damage, and awful discoloration. This is exactly why shipkeeping is such a grueling 24/7 job. The officers have to maintain incredibly strict daily temperature logs, run physical spot checks, and manually verify that their massive floating refrigerators are holding that tiny half-degree margin perfectly steady.
It truly is a delicate dance of thermodynamics and human diligence. Next time you're at the grocery store, I really hope you take a second to look at that perfect piece of citrus or that flawlessly frozen carton of ice cream.
because now you know the immense scale, the exacting science, and the absolute vigilance required by maritime crews to ensure it arrived in your hands exactly as it should. But you know, as global temperatures rise and our oceans get warmer, it definitely leaves you wondering, how long can these floating fortresses of cold keep pushing the limits of thermodynamics before the sea finally wins? Thanks so much for joining me for this explainer, and keep asking questions.